Hello, and welcome to Madison's Chemistry. Today we're going to be going over some practice questions to help you prepare for your Gen Chem 2 final exam. This is by no means comprehensive, but should hopefully be a good reminder of some of the things that you already know, and can maybe help identify some weak points. Okay, so I encourage you as you go along to be pausing this video and making sure that you can do this on your own before you see the answers that I give and the explanations that I give. Okay. So the first question is, if a parent nucleus is X283, meaning that our mass number is 200 and our atomic number is 83, and our daughter nucleus has a mass number of 200 and an atomic number of 84, what type of process is being undergone? So right away you should notice that the thing that's staying the same is our mass number. So remember, the mass number is protons plus neutrons, and that's staying the same. So I know that it already can't be alpha decay, because that is when we release something that's like a helium molecule with 4 and 2. So we would be decreasing the mass number by 4 in the daughter nucleus. So we know that it's not going to be alpha decay. So now we're left to kind of figure out between the two betas and gamma. So the second thing I notice is that the atomic number is changing, right? And so I immediately know that it's not gamma, because gamma basically just has everything stay exactly the same. So it would be like 283 goes to, plus goes to 283. So this is like the excited state, or this is a star. And then this is the ground state. So it's just giving off energy. So we know it's not gamma ray because our atomic number is changing. So now we have to remember the difference between the two. And so for beta decay, we're going to be giving off an electron. So we give off an electron. And here we give off antimatter, which is a positron. And so for beta decay, we will actually be increasing 1 in regards to the number of protons, and we will be giving off an electron. So it would basically look like which is an electron, and our mass number will be increasing by 1. So I think it's beta decay. It would be positron emission if instead of the atomic number increased by 1, if it decreased by 1, then it would be positron emission. Okay. So now let's go off to the next question. So it says, what is the balanced equation of CO3 2- plus NO going to go form CO plus NO3- in basic conditions? So this is a redox problem. So the first thing that I want to do is split it into its 2 half reactions. So this is pretty easy because we can just split it into all the things that look the same, right? So we have the carbons and the nitrogens, and we split those into our half reactions. Okay, so now we have to start balancing this, and this is definitely where it gets a little bit trickier. So the first thing that we want to do is balance all the non-hydrogen, non-oxygen molecules, which in this case it's all balanced. So carbons are balanced and nitrogens are balanced. So we'll go to the next step, which is now to balance the number of oxygens with water molecules. So we can see here that we have 3 oxygens on the left and only 1 oxygen on the right. So we're going to want to add 2 more oxygens to the right-hand side, or the product side. And then additionally, we have 3 oxygens on the product side for NO and only 1 here. So we'll want to add 2 over there. Okay, so now the next step is I have all these random hydrogens that I just added, so I need to balance those out on both sides. So I'm going to be balancing out our hydrogens with an H+. So I added 4 hydrogens now on the CO, so I need to add 4 H+ to the reactant side. And here we'll add 4 H+ to the product side. And so now is when I can go through and I can figure out how many electrons I need. So it looks like, so we need to figure out what the charge is on each side. So it looks like this is +4 and -2. So we get -2 charge, which means that on this side, we're going to want to add 2 electrons to balance out the charge. And then over here, it looks like we have +4 and -1. So that gives us a -3 charge. So in order to balance that out, we're going to want to add 3 electrons to this side. Okay, so now we're going to want to cancel out the number of electrons by multiplying each side by a coefficient. So we're going to multiply this by 3, multiply that by 2. So we'll get 12H plus 3CO3 2 minus goes to go form 3CO plus 6H2O plus 6 electrons, as well as 4H2O plus 2NO goes to go form 2NO3 minus plus 8H plus. So now we're going to want to cancel out everything that we can. So, we're missing +6 electrons. Yep, so our electrons should cancel out perfectly. And then we can now look and see, okay, so H plus, these cancel out, so we'll have a 4 here and then nothing here. And then our waters will cancel out, so we'll have 2 here and none here. Okay. So now, because it says basic conditions, we would basically be done if we just combined like terms here. But we can't have any H pluses in our final thing, so we can't have any of this. So in order to account for basic conditions, what we're basically just going to do is add 4OH minus to both sides. So we'll add 4OH minus here and 4OH minus here. And then, yeah, and the reason for adding it to both sides is if we add something to one side, we always have to add it to the other. So, okay, so, and here, if we have 4OH minus and 4H plus right next to each other, they can actually be 4H2O. So we'll get 4H2O plus 3CO3 2 minus plus 6NO, because I'm including this, goes to go form 3CO plus 2H2O plus 2NO3 minus plus 4OH minus. So last but not least, we will just cancel that out. That's 2, and that should be our answer. So hopefully you got the same thing, and hopefully this was a good review as to how to balance redox reactions the hard way. Okay, now let's move on. Let's go back to acids and bases. So hopefully you guys remember this pretty well, but all I give you is this graph, and I ask for the starting concentration of HA. So you kind of got to remember some important things on the graph. So first of all is that our starting concentration of HA will have the H plus at equilibrium be equal to the 10 to the negative pH. So we know that the pH at the start is 2, so we can find that value right away, right? So we'll get H plus equals negative log of 2, which is 0.01 is our H plus value. And then the other value that we know right off the bat is we have to remember the relationship that at the half EQ, our pH equals our pKa. So I'm sure you guys all remember that in order to find like our acid equilibrium problem, we have to do Ka equals H0 plus times the conjugate base all over a weak acid. But the problem didn't give you this, so you need to solve for it. So here we'll see that the pK is about 3, so that means that the Ka is going to be, I can write that out, Ka equals 10 to the negative 3. Okay, so then if I'm solving this problem, I'm going to put everything into my ICE table, right? And so the thing that I know is the 0.01 because we just found that it was based off that value. So I put in the 0.01 and the plus x is because that's the change. And so this means that the x is actually equal to 0.01, right? And so that means that this increase is going to be the same too, so we're going to get 0.01 here as well. Now that this HA is the thing that I don't know, so I'm going to call this y because I already used x, and we know it's going to be changing by the x value, which is 0.01. So then we can say the end value is the initial concentration, or y, minus the change. So, sorry everyone, this should not say 3, this should be 10 to the negative 3. Okay, so 10 to the negative 3, so we get 0.001. So, okay, so I'll just erase this and solve this with you guys. Okay, so we get 10 to the negative 3 is 0.001 equals times y minus 0.01, 0.01 squared. So we get 0.001y minus 0.001 times 0.01 equals 1e to the negative 5th, which is equal to 0.01 squared, which is 1e to the negative 4th. So we get 0.001y equals 1e to the negative 4th plus 1e to the 5th. So then we get 0.001y equals 1.1e to the negative 4. So if we divide that answer by 0.001, we get y equals 0.11 molarity. So that is how we would solve that. So it's just useful to remember all the relationships in this graph, because I found that a lot of times questions will just give you a graph and you have to remember all the relationships in order to solve it. So remember this titration curve, remember all the points, make sure that when you're studying, you're going back and really thinking about how to read the graph, because obviously with this question, it might seem kind of hard to do when you're only given a graph, but this question wasn't as hard as maybe it looked. Okay. So the next question is, when is a process always spontaneous? So we have to go back and remember, we have to remember that delta G equals delta H minus T delta S, right? So that's our Gibbs free energy equation. And so we also need to remember that things are spontaneous when delta G is negative. So now we need to think, okay, so when is something always going to be negative? Well, I suppose it will always be negative if we take a negative value and subtract it by another negative value, right? Minus another negative. Well, okay. So how about plus a negative, right? So that's exactly what we want to do. So that means that our delta H needs to be negative, so that means it has to be exothermic, and that this whole part of the reaction actually needs to be positive, because it's negative plus, right? So then it's really just negative plus negative kind of a thing. Okay, so anyways, that means that we're going to need to increase in entropy so that it's minus a positive value. So in order to make sure that this is always negative, B is going to be true. Okay. This one, hopefully you guys remember. Okay. So things are a catalyst when they first show up in the reactants and then show up in the products. So NO would be an example of a catalyst, and an intermediate first shows up as a product and then as a reactant, so NO2 would be an intermediate. Okay, and then last but not least, if we add a catalyst, what does this change? So our options are rate constant, rate law expression, and equilibrium constant, and so it can be more than one. So let's first kind of try to think about what exactly a catalyst does. So remember, a catalyst gives us an alternate path to decrease activation energy. And if we remember the Arrhenius equation, the Arrhenius equation tells us that K equals AE to the negative activation energy divided by RT. So this equation tells us that this rate constant K is related to the activation energy. So this kind of gives us one answer. So we know that the rate constant is definitely going to be impacted by the addition of a catalyst because the catalyst is going to change the activation energy. And then secondly, what the rate law expression is. So for rate equals K times AB. So if it's really just K times our reactance, right? So, but yeah, this is the same K. So I think that that's going to be true as well, because if we're